All right, so we're just after 8. Let's go ahead and get started. You should have your laptop for today. We'll need it for 2 things, maybe 3, but 2. 1, you'll need to take your Canvas quiz this morning. And 2, we'll need it for the second half of the lecture where we do our Jamovi Lab, the introduction to the software that we'll be using for the course. You'll probably also need your laptop or some other device if you'd like to take notes that way for the lecture part. All right? So, yes?
Is anybody else having problems getting on Canvas?
Anyone else having problems getting onto Canvas? Is it Canvas in general or the course site on Canvas?
Canvas, for me.
No, check your Wi-Fi. Maybe turn it off, turn it back on. Is it Canvas or just any site? You can get to any site.
Canvas.
Maybe do a Google search, LOU Canvas or LOU Instructure, and that might give you a better link. Next. All right, so quick comment about the quizzes. All right, so this morning's quiz, is this really on? You can hear? This morning's quiz is going to be your standard, typical quiz. You should take it individually, but if you want to work with someone else nearby, that's fine. However, from here on out, the quizzes will be done before you get to class. I don't want to use any class time for the quizzes. Right? So the quizzes at some time after Wednesday will be made available to you, and you get the opportunity to take the quiz up to 3 times. You don't need to take it 3 times. Hopefully you don't. But if you want extra credit, take it 3 times. And the point of the quiz isn't to really test you. The point of the quiz is to make sure that you're seeing the material often enough so it starts to plant and maybe germinate later after you keep seeing it over and over and over again. Okay, so you have the opportunity to take the quiz up to 3 times, and if you do, you get extra credit for taking it 3 times. This is a form of studying, right?
Okay.
That's it. If you don't take the quiz at all, you lose points. Okay? You must take the quiz. So if you take it up to 3 times, you will get extra credit, if they're correct. If you don't get it right, you don't get the points. But you get it correct up to 3 times, you get the extra credit.
So say we scored a perfect score the first time, and we take it 3 times, we still get extra credit?
Correct, yes. Because I want you to keep doing it over and over. Okay, so before we get to class, you went through your notes, you went through the readings, you're ready to take the quiz. Before we come to class, you've already taken the quiz, you've already read, you're ready to go. And I don't want to use any class time for the quiz. I want all of our class time for the lecture and our lab.
Do we get an immediate grade back to tell us if we
You
did
should. Yep,
good?
you should. If that feature hasn't been selected, I'll go ahead and select that feature. But you should get a grade.
Just so that we don't keep doing something wrong.
Understood.
And getting,
Understood.
Cool.
Yes.
So on Canvas, there'll be something that says week 3 quiz,
Correct.
and then we have to do those
Before we meet next week. Right.
Okay.
So in week 3, you'll see a quiz, and that quiz will cover what we spoke about today. Okay? It won't cover the readings for week 3. It'll cover what we did today. So I want you reviewing, refreshing. I want you to have that solid base before we start with new material. Okay? So this is a way for us to kind of hedge against the procrastinators in here. All right? I know you're busy, you have a lot of material to cover before you finish up and get out and go practice, but I want to make sure that this isn't one of those classes where you feel, I don't really need to stay on top of it, I'll kind of wing it for the exams. Yes?
Go ahead. You guys waiting? Oh, okay. Sorry, sir. Quick
Yes.
question. For example, if we get 4 out of 5 on a quiz and there's 3 times to take it, if we take the 3 tries, if we retake it 3 times, and we get 4 out of 5 on the first one, what would be our score on the third?
That's a good question. So, am I making a differentiation between whether you get them correct or not? No. So, if you really want to piss me off, you just go ahead and take it and not even care what your score is. Just pick a random answer, get them wrong 3 times, and get the extra credit. That's on you. That's not on me. Okay? But if you really try your best and I got first time 3 out of 5, next time 4 out of 5, next time 5 out of 5, you still get the extra credit. Okay? Or you get 3 out of 5, 3 out of 5, 3 out of 5, still get the extra credit. Because it's going to be in your mind, why am I getting 3 out of 5? You're going to talk to your other classmates and figure out, hey, what'd you get for the other question? Why did I get that wrong? And it'll stick. And by the time we get to the midterm and the final exam, you'll have it sorted out. Okay, so I'm not making a distinction right now for whether you're getting the quiz answers correct. I'm making this distinction of are you reading and are you trying on these quizzes? Are you at least seeing them? If you don't try at all, yes, you will lose points. So if I see that, oh, you've done 0 out of 3, you'll lose points. Justifiably. Yeah. Sorry, that came down a little, a little harsh, but
Thank you for the clarification.
you bet, you bet. Any other questions? All right, so without any further delay, let's go ahead and jump into that quiz on Canvas. There's a code for it, and it's transparency with a capital T. Transparency. 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 Let me know if you're having any difficulty getting into the quiz. And you can work together with someone nearby. No, just take it once. Just take this one once. The option is on there to take it 3 times, but you won't get the extra credit. Well, for the following quizzes, yes. Transparency.
Capital T.
Capital T, thank you.
Oh, sorry.
All right, so do you remember that slide from last week where we talked about the relationship between signal and noise? Every single statistical test is that ratio of signal to noise. Signal in the numerator, noise in the denominator. And our goal is to try to minimize the noise in the denominator so we can see the signal in the numerator. And if that happens, we have a real signal. If that doesn't happen, okay, and instead what we get is that the denominator, the noise, is bigger than the signal, then we have random variation or random error or chance differences. These aren't real differences, not the kind that we're really interested in. Okay? Question?
From last week, some question. Can I ask about it?
One more time, louder.
Slide 39.
Correct.
That's the table about alpha, beta. So what are those?
For the
I didn't understand.
alpha, beta.
And then 1 minus alpha, 1 minus beta.
Oh, where are you getting this?
39.
39.
From last week?
Last week.
Okay.
Table.
Hang on.
It's only decision errors.
Oh, we're not there yet.
Okay.
Right, we're not there yet. So when we make a decision, the question was about the slide where we're talking about decision errors, alpha, beta, 1 minus beta, etc. What are those? Statistically speaking, and in reality, since none of us really is a deity that knows everything, every single one of our decisions are gambles. They're probability estimates. Whenever you make a decision, you might be right, you might not be right. Statistically, when we say we might be right, we might not be right, we try to add a probability to that. So there are 2 kinds of errors that we make in life. The first error is when we say something is there when it really isn't. Okay? That's the first error. That's called alpha error. Saying something exists when it really doesn't. The second error we might make is saying something does not exist when it really does. So again, for the first error, alpha error, saying, hey, this treatment works, but it really doesn't. A beta error would be, this treatment does not work, but it really does. Okay, so those are the 2 kinds of errors we might make statistically, and we need to add probability statements to them so we have an idea of, am I comfortable with this kind of alpha error? Am I comfortable with this much beta error? Once we attach some numbers to them, it makes it a lot easier for us to determine whether I want to move forward with that treatment or whether we want to hold off on that. Okay. What is the likelihood that I'm going to make an alpha error here? It's very low or it's very high. What's the likelihood that I'm going to make a beta error? Very low or very high? Very good question. Okay, so that is our quiz. We want to move to the first part of our lecture where we discuss research design, central tendency, and dispersion. You're also taking a research course with Dr. Kwan. Dr. Kwan has asked me to lead you in a lecture of research design. So what I'm going to do in our stats course is give you a very brief overview of research designs and how they impact our statistical decisions before the nitty-gritty granular discussion about case control versus cross-sectional versus cohort versus experiments. We'll leave that for your research course lecture, okay? So we don't have to do that twice. Then we'll segue into a discussion about, sorry about that. We'll segue into a discussion about measures of central tendency and dispersion. Okay, so these are descriptive statistics. I believe next week we're going to go in more detail, but I'm hoping that we don't have to use an entire lecture to talk about mean and standard deviation. In fact, you're supposed to have come into this class with that knowledge already. So we're going to have a very brief discussion about central tendency and dispersion. Your readings have gone into detail about central tendencies and dispersion. So what we'll do in class is brief overcap and review, and then show you how to do that with the software. Okay. And then we might be able to get ahead of schedule and actually spend a bit more time on our group project and preparing for the midterm and final exams. Okay. Then we'll take a break as we discussed. We'll take a break, and then we'll pick up with our Jamovi lab, and then a quick highlight for what we'll be discussing next week. Second thing I want to introduce you to as well is, do you remember the statistical methods text that you were required to get by Cheryl Willard? It's a workbook, and it kind of takes you step by step through the calculation and the building of all the statistical procedures that we're going to be working through in this course. Okay, it's required. You have to have that. You have to do it. If you don't do it, you'll get a 0. Okay? If you do it, you get extra credit. There's no middle. Okay? It's required in the sense that if you don't do it, there'll be a 0 for the required readings. Okay? If you do it, you will get the bonus points for doing it. There's no way you can do this course without doing that workbook. But I'm not going to spend time on that workbook. So at some point in this class, doesn't have to be now, doesn't have to be next week, but at some point before this class ends, I need to see that workbook completed for you. Okay? So it's up to you when you want to do that.
So, is it, do you want us to write in the book?
Write in the book or print it out, and you write on the printouts, but you need to complete it.
Or because I have the book, but I don't want to write in it.
At
I
some
can just write on a paper.
Write on sheets of paper, it doesn't matter. But at some point, I need to see that you've gone through step by step to understand what was driving each of these procedures. It's very, very easy. Every week, I'll be submitting the answers to the exercises in the workbook. So there's no reason why you shouldn't be able to kind of look at that and start to transcribe that into the book.
The whole, like,
No, not the whole book. So every week I'll tell you which chapters are relevant to what we're talking about, not the whole book. We're probably going to get through about 2/3 of the book. We don't do the entire book. Okay, but there's no way to understand these procedures without having done the step-by-step. Yes, question in the back.
So at the end of the day, you'll give us something to work on?
So it will be uploaded into Canvas, which chapters are relevant to what we're speaking about. And so next week we start with the central tendency and dispersion. So we start getting to chapters 2 and 3 and 4 in Cheryl Willis' text. And you just go through there and you follow along, and complete it. And at some point, whether it's weekly or by the end of the course, I need to see that you've completed that textbook up to what we've agreed to.
I could just get a notebook and then turn it into, right?
Absolutely. I won't take it. I just need to see it. Yeah, I don't like collecting paper. Okay. If you do it on your laptop, if you do it on your iPad and want to show me, that's fine too. But at some point, you need to show me. Okay. Fantastic. All right, so let's move right into it. Today we want to prep the discussion for research designs and how different research designs allow us to characterize something that we don't know. We'll call that uncertainty. Okay, and then what the research projects allow us to do, is it just me or is it warm in here? It is warm. If you don't mind, I'm going to take this off. So these research designs, what they're able to do is they're able to allow us to characterize what's not known. But the way they do so, because we have different research designs, some research designs do that really well, some research designs not as well. Okay, so we're going to talk about that. But let me give you an example. Here's a study that was conducted by some colleagues at my alma mater at WashU and also up at Stanford. And what they did was they had access to Facebook data. Facebook data. Thousands of users of Facebook data. And the question that they had was, how accurate can a computer model be to judge the personality of humans? And they compare that with humans judging the personality of another human. Okay, so some of you in here know each other, you're friends. Some of you are maybe roommates. I don't think there are any spouses here. Or maybe someone's dating someone else on this campus. But if you think about the different relationships that tie people together, you can think about how intimately you know someone else. The goal here was, if we just look at your Facebook data, right, would we know you as well as other people in your life? Now, it's not just all kinds of Facebook data. They were very specific. They said, we only want to look at things that you've liked on Facebook. Okay, so what we have here is a diagram, and it's got an x-axis and a y-axis. Okay? On the y-axis, we have accuracy. How well the two agree with each other. So if it's the computer model, or if it's, let's say, the friend in your life, there's something true about you. The question is, how well does a friend know this about you? And this would be called correlation. Are the two correlated? The way you responded to the questions and the way your friend responded about you to that same question. And along the x-axis here, we have is number of Facebook likes. So how well would we know you with very few Facebook likes? How well would we know you with quite a few Facebook likes? So here's what we have. The human average with about 100 likes, we have a correlation coefficient of 0.49. Now you're asking yourself, 0.49, is that big, is it high, or is that low? What does that mean? These correlation coefficients range from 0 to 1. And the closer to 1 you are, the more perfect the agreement between the way you responded and the way others in your life responded about you. A score of 0.49 is really, really good. It's hard to get up to these 0.8 and 0.9 correlation levels. We only see those really biologically. For example, does a blood pressure in the torso, does it correlate to the blood pressure in other parts of the body? They're very tightly related to each other. So we expect really high correlation coefficients there. But here, when we're talking about, let's say, personality, the way you respond on questions, the way others respond on questions, that's not necessarily biologic. This is psychologic. So the fact that we see correlation of 0.49 is really, really good. Okay. How many likes do you think Facebook needs in order to do as well as a work colleague? Okay. So Facebook has access to all of your likes. Then they ask people that you work with questions about you, right? How neurotic you might be, how open you are, how extroverted you are. Your work colleague has an idea about you. Facebook only has access to your likes. How many likes does Facebook need to know you as well as a work colleague? 200? 10. They only needed 10 likes to know you as well as a work colleague. And again, liking anything, it's not liking something specific. 10 likes on average is all Facebook needed to know you as well as your work colleague. I'm going to say know you as well as is to know you as well as how open you are, how agreeable you are, how extroverted, the 5-trait average in terms of the big 5 in terms of personality, conscientious, neurotic. These are major personality characteristics. Right? This is I don't know, I can't tell from your expressions if you're freaked out or not, but this is with only 10 likes. How many, anyone here on Facebook or was on Facebook? Have you liked more than 10 items on Facebook? Facebook probably knows you as well as your work colleagues. All right, what about your friends? 30 likes? 70, okay? With 70 likes, we're starting to approach that average. With 70 likes, Facebook knows you as well as your friends. Okay? What about your roommate? Think it would be any different than your friend? Probably not different. It's a good guess. 70 likes as well. And the correlation coefficient here is at 0.45. What about family? All right, this is starting to get a little personal. 500. Okay. 150. Only 150 likes is needed for Facebook, or at least for the model that they built, to know you as well as your family does, with a correlation coefficient of 0.5. It's amazing. What about spouse? Anyone here engaged or married or long-term significant other? Okay. Well, you might reconsider. 300 likes. Facebook can know you just as well, so what's the point? Get involved with Facebook, right? 300 likes. Has anyone, how long have you been on Facebook? Years. Definitely more than 300 likes, right? 300 likes is all Facebook needs, or at least the model needs, to know you as well as a spouse does, in terms of how agreeable, how neurotic, how extroverted or introverted, the big 5 in terms of personality characteristics. This is freaky. 300 likes. Now, is this magic? It's not magic. When you're liking something on Facebook, and indirectly when you're not liking something on Facebook, but when you're liking something on Facebook, there is a pattern, and that pattern is related to those characteristics about you. That pattern is mathematical. And if it's mathematical, that means that pattern is something that statistically, with enough data, it starts to look like a signal. And if it starts to look like a signal and it becomes consistent, now you can build a model for that. There's a question.
Yeah, I was going to ask, how does the computer know what you're liking or not? Like, how does it differentiate between a car or a dog? Or, you know,
It isn't.
Okay.
It isn't. Okay, so whether you're liking baby photos or animals or gun ranges, schools, illicit things, it doesn't really matter. What matters is the fact that there's a pattern there. And that pattern, when they look at other people like you, those characteristics start to pop out. Now, Facebook isn't saying, oh, that's neuroticism, or that's agreeableness, or that's the big 5. We put that in. So we look at the data and we say, wait a second. The shared component here is neuroticism. The shared component here is, all the things that we identified. And in fact, you, or if you participated in the study, and the others who participated in the study did complete questionnaires specifically for those characteristics. So when you mathematically look at the characteristics and their pattern, and you look at the likes and their pattern, and other people like you and their pattern, that's why Facebook is saying, look, there's enough information in the data to say that only 300 likes is enough for us to identify the characteristics about you with others. So it doesn't really matter what you like. If enough people like that with those shared characteristics, that pops out as a signal. So the beauty here, the power here, isn't so much that they have your data. The power here is that they have thousands and tens of thousands of people like you and their data. They can reduce that down to these very simple models. This is the issue of power and sample size in statistics. When you have enough data, it's easy for us to do statistics. That is, to characterize an unknown. Incidentally, when we take the humans in your life, and we average these guys, and compare them to the model that Facebook built, their model outperformed the average of the humans in your life. That is, the correlation coefficient is 0.56, which is more than the 0.49. Okay? That is amazing, and that is the power of data, having loads of data at your fingertips. That Facebook study is an example of what's called a cross-sectional study. A cross-sectional study. What they did was they had you and others complete questionnaires, and also you have data that already existed. So when you collect all of that data at the same time, that's known as a cross-sectional study. Okay. When we try to follow people over time, that's known as a cohort study. So for example, if Facebook started and say, hey, look, you're our first 10,000 people to participate in Facebook. 5 years later, we are now going to try to determine if where you're at 5 years later was related to anything that you were exposed to earlier on. That would be a cohort study. Okay? A case control study would be people who ended up going to dental hygiene school or dental school versus people who did not end up going to dental hygiene school or dental school. How were they different in undergrad? That would be a case control study. I start with the two groups of interest, and I kind of work backwards to find out how were they different to begin with. Okay? What you'll notice is this arrow, and this arrow is going down the studies because what I'm indicating is that the strength of evidence for causality, that is, once you're exposed to something that leads to an outcome, X causes Y. The only study that can really do that, it's not the cross-sectional case control cohort, these are all observation studies, it's only the experiments. When you get to manipulate the factors under consideration. Okay, so if you are responsible for the exposure, it's unethical, but here, you smoke for 10 years and we'll see what happens. And you don't smoke for 10 years and we'll see what happens. If you're responsible for providing the stimulus or providing the intervention, that's an experiment. It's the best way to look at cause and effect. But if you say, hey, tell me if you've smoked for the past 10 years, and you ask another group, tell me if you smoked for the past 10 years, that's an observational study. You aren't responsible for their smoking. It's still good evidence, but it's not the same kind of evidence as what you get from an experiment. You start, and then you follow to see what happens. Even a cohort study is not as strong as an experiment, and here's how. With a cohort study, I can take a group, right, and say, hey, smoke, and then 10 years later, we'll follow and see what happens. But the experiment says it'll take the group and it'll randomize who smokes and who doesn't smoke. And that randomization piece is what allows us to say, remove any random error so that any difference that we see is due to a real signal. Okay, so the experiment is the only way to really look for cause and effect. We get pretty good data for that from these other study designs, but the only study design that allows for cause and effect, hint, 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 triple underline, asterisk, asterisk, asterisk for quiz next week, the only study that allows you for cause and effect is the experiment. No other study design. All right, so when we have these different study designs, they're meant to be able to give us statistics. Here are our statistics, things that we like to be able to measure. Say a mean, a median, standard deviation, a range. Okay? But in order to be able to measure these statistics, we have to look at what kind of data do we get. And there are, let's say there are 3 types of data that you're going to be concerned about. The first is nominal data. Okay? So when we look at who were the people that participated in that Facebook study, there were coworkers, roommates, friends, spouses. They only differ in name, those different groups. Okay? That's a nominal data. But if we said, wait a second, no, it's not just nominal data. Let's say that those differences are related to intimacy. Let's say you could rank them in terms of intimacy. Okay, well, the least intimate group would be your coworkers, followed by who? Your friends and roommates, followed by who? Family, followed by who? Maybe a spouse, right? So if you ranked the data that way in terms of intimacy, you have what's called an ordinal data. We haven't really specified how much intimacy separates the different levels, right? We simply just said one has lower intimacy or higher intimacy than the other. Okay, so that would be an example of an ordinal level measurement, let's say intimacy. And then the ratio level would be if we could actually calculate, let's say, intimacy. Let's say as a proxy for intimacy, we said, how long have you known the person? That may not necessarily be a direct proxy for intimacy. A lot of times you get involved with someone or you marry someone who you don't know as long as someone that you've been friends with from childhood. That's rare. But the years of knowing someone is a ratio level variable. And we say it's ratio level because a 0 for it would be a true 0. Have you met this person before? No, I've never met them before. So how many years have you known them? 0. That's a true 0. As opposed to maybe in physics and in chemistry, you can have a 0 for certain measurements where that 0 in terms of temperature doesn't necessarily mean that there's no temperature. 0 degrees Fahrenheit, 0 degrees Celsius does not mean no temperature, right? It's just a midpoint on that axis. But in terms of energy, 0 degrees means there's no energy here. Okay? Question?
So, ordinal is based on intimacy, interval based on, what did you say, age, knowing?
Right, so if we looked at the Facebook study, nominal would be the different kinds of people asked to participate to answer questions about you. So colleagues, friends, spouses, roommates. So that's a nominal level data. They differ in name only. Different name only. If I asked you guys, which region of the US are you from? West, Midwest, South, Northeast. Now I'm biased. I do consider one of these regions to be better than the others, but I can't do that. They only differ in name only. Okay? So ordinal would be, well, let's rank. If we rank the region of the U.S. by population, say the most populous, followed by the next most populous, followed by, and so on. I'm not giving exact numbers, but I am ranking them in terms of position. That would be an ordinal level variable. So just like the Facebook study, if we said, don't treat the people who are participating as just nominal. Let's say that they differ in terms of intimacy, right? Level of intimacy. Then say, okay, the spouses or significant others, they know you the best, followed by longtime friends, followed by co-workers. That would be an ordinal way of ranking the people who participated in the Facebook study. Then the ratio level, let's say we calculated or asked you, how long have you known the person? So years of knowing the person. That's ratio level. Because you're actually getting a number. How many years or how many months have you known this person? And that number is considered to be what we call ratio.
I mean, the example of like you're doing the United States of East, West, populous, interval ratio would be what?
Interval ratio, so for example, if we were, states doesn't really lend itself to ratio level. But if you ask the population for each state, right? If you ask how many residents do you have, then every single state would have to say, well, we have this number. That number, the number of people in your state, is a ratio level measurement. Does that make sense?
Yes.
Perfect. All right, so when you have this different kind of data, it kind of dictates what you can do with the data. So when we want to talk about central tendency and dispersion, first name and last name for a measurement. When you have nominal data, you can only give mode, and the mode is the most frequent observation. So for example, if I asked where you guys were from, West, Midwest, Northeast, South, whichever region is the region that has the most of you, that would be the mode. How many of you are from the West? How many of you are from the Midwest? Only one. Where?
Nebraska.
Ooh, and where?
Nebraska, sort of.
Oh, what? You don't know each other. Not that many in
No,
the
I know
past.
who that is.
I went to school in Missouri. I love the Midwest. I mean, from the South. Only one. Oh. Where?
Florida.
Florida. Okay.
Yeah.
Northeast.
Connecticut.
Connecticut and
Massachusetts.
Massachusetts. Thankfully, no Jersey. Excellent. All right. So, where's the mode for the region that has the most DNHY students? The West. Okay. If we wanted to look at the ordinal level data, measures of central tendency that we can use for that are median or the mode. We use the median because the median has more information than the mode. Mode simply says west is the most populous. But the median would say, well, if we ranked and said which region had the most population, followed by the next region that had the most populous, followed by the next region, etc. If we rank that way, we could then say, okay, we've got the West followed by the Midwest, followed by Northeast, and then the South. Okay, so we can find the median. We'd be asking ourselves, where would the median for that rank order be? The median most likely would be between the West and the Midwest. Okay, because of the bulk of how many of you said you were in the West. So we're just looking for where the median lies, and it's between the West and the Midwest. That would split the distribution in half. And then for ratio, we prefer to use the mean as opposed to the median and the mode. Although we can calculate it, we prefer the mean because it's got more information. And with the mean, we call it ratio level because we can actually do statistics, meaningful statistics with it. Like signal over noise. We can do addition, we can do subtraction, we can do multiplication, we can do division. We can only do that with the mean. We cannot do that with a mode. It's tougher to do with a median. Okay, so the mean is the most significant measure of central tendency because of how much power and information it has. Well, that's the first name, central tendency. Where is the middle of the distribution? The dispersion would be how much variability is there around that middle? Or what kind of variability is there around that middle? So the measure of dispersion for a mode is simply the percent distribution. So if we said that the most frequent region of residency here is the West, the question would be, well, what proportion does that represent? So here it might be like 70% or 80%. 80% of you say that you're from the West. If we ranked order and said, well, where's the median? Well, the median is between the West and the Midwest. We might want to give a minimum and maximum, that is the number of participants who said they were from the West, number of participants who said they were from the Midwest, or we can give a percent distribution of percentiles. Again, the proportion that said they were from the West, the proportion that said they were from the Midwest. Then finally, for the ratio level, when we use the mean, we want a standard deviation. Now, the calculation of the standard deviation is you have a middle, go back and take every single score and find out how far away that score is from the middle. It's called a deviation. So some of these deviations are going to be negative, some will be positive, right? Because you've got a middle. So if I add up those deviations, what would I get? So assume that the distribution is nice and symmetric, bell-shaped, right? Perfect middle for where that mean is. And then I add up the deviations for all the negatives and the positives. If I add those all up, what should I get?
10%?
10%?
Yeah.
No,
Oh.
not 10%.
Oh.
I'm adding up all the deviations. So I've got a middle. Let's say I've got a score here from the middle. So I say this score minus the mean is something. It'll give you something negative. Then I take the next score. That minus the mean. Then sorry?
Is it the variance?
Not yet. We don't get variance yet. But I'm just looking for a number. I'm looking for a conceptual number. As you think about it, it's like, wait, that's the middle. If I take everything from down here that's negative and add that to everything up here that's positive,
50.
what would I get? 0. Very good, 0. Because again, you've got a middle point. It's perfectly balanced. The mean is that perfectly balanced middle point. So if I take everything to the left of the mean and subtract the mean from it, I get all these negative numbers. If I take everything to the right of the mean and subtract the mean from it, I get all these positive numbers. But because that's the middle, if I add up all those negative numbers with the positive numbers, I get 0. Well, that's not very meaningful to us. So what we do is we go back to that calculation, we say, okay, take all those negative numbers, instead of leaving them as negative, take each one of them and we're going to do what to them to make them positive? Square them. I'm going to take the score, subtract the mean, and then square it. Go to the next one. Take the score, subtract the mean, and then square it. Take the next one, take the score, subtract the mean, square it. Now all those negatives are positives. Okay? But then I have to do the same thing on the other side too. So I go to all the positive numbers, subtract the mean, square it. Next one, subtract the mean, square it. They're positive too. So now I take all these used to be negative numbers, they're now positive. They're bigger, but they're not positive. And I add up all these positive ones, they're just bigger positive numbers. I add all of those up, and then I divide by however many numbers there are. Right? That is very, very good. That is variance. But the units for that compared to the mean are what? It's units squared. Fantastic, you guys are on the ball. It's units squared. So that's a little tricky. I've got a mean that's got regular units, but then I'm trying to build this average amount of deviation or variation where I'm subtracting the mean from all these scores, and then I square it, and I divide by however many there are. So now I get variance, but the units are squared. What do you do to a square to get rid of the square? Take the square root. So if I take the square root of variance, I'm left with standard deviation. That's how you calculate standard deviation. Take the variance and take the square root of it. And how did you get variance? Well, I took all the scores. Doesn't matter if they're on the left side of the mean or the right side. I take all the scores. I subtract the mean from all of the scores. I add them up, and then I divide by however many scores there are. That's variance. Very intuitive, but it doesn't match my mean. So I take the square root, so the units match. Now the units for mean and units for standard deviation are the same. And that's why we report standard deviation with the mean. Conceptually, kind of follow that? Okay, so in your practice, you're going to be doing that by hand, just so that you kind of get the idea. But in class, we're going to move straight to, you guys already get it. Let's go ahead and use the software and see how we do that with the software. Any questions so far? Yeah, we're moving kind of quickly.
And
Yes?
another question. So the book goes through all this, right?
Yeah. Yeah. The book goes through all of that, and you get a lot of practice doing it. You will do it very well. So a little bit more about the median, because now it matters. You're dealing with a patient, and the patient has some questions about you for some of the things that you're saying. And you're using statistics. You might be using means. You might be using medians. This is Stephen Jay Gould. Was a Harvard professor of paleontology, biology, natural history. He unfortunately was diagnosed with a fairly fatal cancer in which there's an 8-month median for survival. That's what his doc told him. Now, he's educated, so he says, look, I know that just because they told me that I have an 8-month median for survival does not mean that I only have 8 months to live. Because you understand, just like he understood, that a median simply tells you where the middle is. So if I take a distribution and I tell you where right in the middle there is, that is, to the left is 50%, to the right is 50%, that doesn't tell you, right, what the average is for that lower 50% and what the average is, or the mean is, for the upper 50%. So he said, well, I want to know, for the half of the people that live longer, what are my chances of being in that half? So he read all the studies that he could, and this is what he found out. That looked pretty good. He had every one of the characteristics that conferred the probability of a longer life, meaning he was most likely going to be in the upper half of that median. Okay? So he was young. The disease had been recognized at an early stage. He would get really good treatment. He was optimistic, right? And he wasn't going to despair. So he had a lot of the characteristics that said, although your cancer has an 8-month median for survival, Those that are in the upper half actually tend to live quite long, especially if they get good treatment. And that's in fact what he did. I think he lived for another 18 years or so after this diagnosis. Right, exactly, with an 8-month median. So it's really important that when we talk about central tendency, that we really understand how to interpret them. Because we don't want a patient coming away thinking that whatever treatment you provide means that they're going to need to visit you again in 2 weeks or 2 months or 2 years. That just might be the median survival for, let's say, for an implant or for some other treatment. But really what we want to find out is, are you in the lower group who's going to need to see me 2 months from now or 6 months from now? Or are you in the upper group who maybe we can wait another year, 12 months, or 16 months before we need to see you again? So that brings us to our discussion of the main challenges for dental measurement. These would be getting accuracy and precision. Okay, accuracy and precision. Now you might have seen these targets before, where to the right-hand side we have greater accuracy, right? To the left-hand side we have lower accuracy, and at the bottom we have more precision, and here at the top we have less precision. Where do you want to be as a dental clinician?
Bottom right.
Which of these 4 targets do you want to be? Bottom right, where you have more accuracy and more precision. But let's talk about the scatter around these, so we have an idea of what things look like. In the top left, when you're dealing with something, a measurement or a situation in which you don't have a lot of accuracy and you're not very precise, this is the scatter that you would expect. Okay? Let's go through that. How do we know that this scatter is not accurate? Right, and you're not close to the bullseye. Here's the bullseye, right? Accuracy is you're far away from the bullseye. Okay? How do we know that this scatter represents low precision? So you're not very precise. Yeah, all the dots are kind of separated from each other. So the fact that they're not clustered with each other shows that they're not precise. Okay, so they're not accurate because they're not close to our target. They're not precise because they're not close together. So when you see a scatter like this indicates low precision and low accuracy. What about when we increase the accuracy? Is this what you expected to see? Describe the scatter for me. How do we know that this represents more accuracy but low precision? They're closer? Closer to what? Closer to the target. So we have more accuracy in the sense that if we were to take the average for all these guys, the average will put us where? Somewhere around here. Right, exactly. So that's closer to our target than before. Well, what about precision? How do we know we don't have precision? They're still scattered about. They're not clustered together. Okay, so now when we look at the bottom row for precision, what do you expect to see in terms of scatter on the lower left? Closer together, and where in terms of accuracy? Closer to the center? No. Still far away from the center. And in fact, well, I'll start on the other side. So here's what we expect for a high accuracy, high precision. And then for the situation that you just described, we have precision, but still not very accurate. This is an example of some kind of bias. Actually, this is bias too. When you're not close to your target, this is indication of a bias. Okay. Sometimes the bias is systematic, right? So it's all kind of clustered right there. Sometimes the bias is kind of random and has us all over the place. Okay? But it's still bias because it's getting us to one section of being away from where the target is. And the precision here, you can have precision or randomness that on average gives us a pretty good idea of where the middle is, or where we want to be. Okay? This precision is not as bad as this lack of precision. This lack of precision still has us far away from where our target is. But this lack of precision, right, at least coupled with this accuracy, gives us a pretty good idea of where the middle is. I can handle this lack of precision. I'm having difficulty with that lack of precision. A couple more comments about bias, and then we'll take a quick break and then launch into Jamovi. So we understand that we need to take measurements, and that as dental clinicians, you want both accuracy and precision. We also understand that when it comes to understanding where to use these procedures, right, there's one more thing that we need to take into consideration. And that's, we were talking about it before, and that's when you're interacting with another patient. Do you have an idea who this is? Yeah, younger version. Yes, Gandhi. If I were to ask you how old he was when he died, some of you might be able to tell me. Some real nerds in here. You might know. But if you don't know, I would bias your results if I were to ask you if he died before or after the age of 9. If I asked you that and you didn't know, you're more likely to give me a younger age at which he died than if I were to say, did he die before or after the age of 140? That group would give me an older age at which he died, again, if you didn't know. So when we talk about trying to get data, trying to understand data, especially with survey methodology, and we're trying to, again, characterize an unknown, there are inherent biases, like this one called the anchor effect or anchor bias, that kind of screw up the data that we get from our environment. So we have to be really careful, if you're concerned about accuracy and precision, you have to be really careful about how you get your data, because the method that you use to get your data might inherently bias the results that you get. Do you kind of understand that? Okay, so we have to get clever enough to figure out how are we going to measure our unknowns so that we don't unduly bias the results that we get. So this, you have this, I don't think we need to go over this more. This is just review for you. What I want us to quickly transition to is here. Noise is represented by this kind of scatter. Okay, so here we're noisy and unbiased. Here, precise but biased will give you this kind of scatter. And I want you to really understand these two situations, because these are the two situations that clinically you're most likely to deal with. Measurements that are noisy but unbiased, or measurements that are really precise but still need to be calibrated. Okay? So just because you have precision does not mean that you're calibrated. Just because you're noisy doesn't mean that you can't still work with it. These are the two situations that clinically you always need to be mindful of when you're reading studies or when you're conducting experiments or you're interacting with someone who's trying to sell more techniques or sell more tools to you. These two situations you have to be mindful of. All right, let's take a quick 2-minute. Do we need more than 2 minutes? Some are saying yes. Okay, 5 minutes. Let's take a quick 5-minute break. If you haven't already, download the Jamovi software, get it up and running on your laptop. I can show you how to use this to understand central tendency and dispersion. Yep. Bring it up along. Let's take a look.
Where do you get the
Okay, it's in, not sure. It's in your syllabus. Because you can still here.
I'm over there.
Right. But,
Oh, so how do you
Did you download Jamovi? How did you do it? The link is in his syllabus.
there you go. So download that, install it. Shouldn't take you more than 5 minutes, and we're ready to go. You also need to download the file. So for this week in the module, there's a file.
How many numbers repeated?
So the mode is which is most frequent. So you have different levels of responses. Which one of these levels is most frequent?
Means the famous one, the face number.
Sure.
Yeah, okay. So the median is the highest one and the lowest one.
No, it splits the distribution in half
Half, based on what?
based on your measurements. So
Okay, I got it.
yeah, so for
Should we find it or no? I know it's in the middle, but
if you have the data by hand, yes, you can. But if you solve it, the software will tell you, here's the median. This level splits the distribution.
got it. And then mode is the
Observation.
oh, got it, yes. And then mean.
This is just telling you that with this kind of measurement, you can only measure light. With the ordinal, you can measure median and mode. With ratio, you can measure mean and mode.
Thank you, sir.
Yep.
Okay, so
Now that's the actual test. Now you want the software.
okay, so not the text.
You want the test because that's where some of the readings are.
Okay.
But we need the software to do the
Okay, so I need them
for later for the readings.
later.
But do you have the software?
Yes. Okay, great. Thank you. My husband is in year 2.
What's his name? Same last name? For the pickup. For the pickup.
Good, do it. Tell him I said that.
This one. Well, no, keep it. This is very good. I really need to focus on it. Yes. So here's a situation where it's precise, but it's not biased. It's biased because it's not close to the part. You're far away from the truth.
So they're like.
Yeah, so although it's precise, they're biased because it's not close to the truth. So here, it's unbiased because it's still kind of circling the truth. So if I took the average of these, it'll still give you the truth. But it's noisy because so these are the two situations that you're most commonly given.
Other than the like, this is
No, you don't need another form. Yep. Just know that there's biases like this tend to influence the way we get data. So data isn't really pure. The way we measure often gives biases that will tend to be line-based. So if I say, well, it was before I'm the age of 9. Once I tell you 9, you're already thinking lower numbers. So when you do something you don't know, you say, oh, well, you told me 9, so you might say something. If I say, was it closer to the age of 4 years old, maybe it's like 80 years old. So even these numbers, portions of it. They're like personality types of No, the computer can't think that way. It's patterns. So your job as an investigator is how they build the Myers-Briggs to say, look, if we ask them these kinds of questions, and these kinds of questions map to these lines. Well, if you know someone's personality, it builds
Yeah, I do it every morning.
Well, many of us are influenced by influenced by those the groups that used to be. So what was happening with foreign groups is that they would populate those groups with a lot of propaganda and really give people a lot of because it works.
No, I am.
Yeah, because it works.
You know which one's the fire that we need to count?
I'll tell you when.
Yeah, go to this module.
Yeah, this is mine.
Oh, no,
You know which one is the fire that we need to count? This is inside that. What, both parts? Or the CSB?
Okay, but the assignment one is something that you turn in for next week.
Yeah.
We need.
Thank you.
No, it's not chapter one that has a lot of prior stuff. No, which book are you doing? Okay, yeah, so that one is chapter 2, which is start with sensitivity. They're separate. There's 2, 3, and 4. Chapter 4 really starts with 2 and 3. Sensitivity and All right, so you have Jamovi up and running, ready to go. You should have a screen that looks like this with your software. It won't be exact, but it should look something like this. There is a file that you need to download. There's a file that you need to download. Did you download it? It's a lab file. It's called a CSV file. Okay, if you downloaded the CSV file, how many of you have downloaded the CSV file?
Where does it say CSV?
In this extension.
What is that?
It'll say lab blah 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 dot CSV. Anyone have that?
Yes.
Okay, good.
Should we open it?
We should open it, but I'm going to show you the steps. So I'm going to exit out of the PowerPoint, and I'm going to go down to my Jamovi. Now, I'm doing the same thing with the pre-docs. So ignore the fact that mine is called DNES. Okay? Yours is the same. So I'm going to show you the steps by which you go through to upload the data into Jamovi. Okay? So here at the top left, you see those 3 horizontal bars?
Yes.
Okay, those 3 horizontal bars, you want to click on that and bring up a drop-down menu. And that drop-down menu should have these following options where you want open. Okay? Anyone not getting that? Well, we're doing well so far. So you go to open. Go to open and then navigate to where you downloaded that CSV file. Navigate to where you downloaded that CSV file. We good so far? Okay, that tells me no. Maybe we need to go back a couple steps.
I got
Question? Send?
You might need to help me help her.
Okay, a little bit louder.
So I click on open.
Wait, I'm having difficulty hearing Sandra.
I'll ask her.
No. One more time. I'm sorry. Was it Sarah? Not Sandra. Sorry. Fail. Sarah.
Oh, no.
Sarah.
So I click open.
Click open.
Yes, but we showed up something like B5, road, bogs, something that is I don't know.
Okay, so you still need to navigate to your file.
Just drag it.
Yeah, just drag and drop it.
Okay, so there are a number of options here. You can drag and drop. You can navigate to the file. Yes.
Yeah, you just drag and drop it into the Jamovi.
So I'm going to show you what to do. So I'm going to go to my desktop.
Does that have fun? Yeah.
You guys have it?
Well, she's saying that when she pushes open and then goes to this PC address, it has options already in there. Yeah.
Oh, forget about the options. Go ahead and find your file. You can drag it over and put it into Jamovi and it'll open it. Or you can navigate to the file and open it. If you know where your file is.
No way. Okay, there we go.
All right, so what I'm going to do is I'm going to take a minute to pop around to see if I can answer more specifically some of your issues. Anyone have any?
I hate it when computers are like giving you anxiety. It's like you're a Mac.
You gotta close some applications. There's a lot of
Yeah.
yeah.
Like, oh, like these?
I told you. Check your partnership. I am.
That's difficult.
Don't give me that.
Don't look at me. Is it worth it?
I'm gonna go to your house and we're gonna watch it.
She did last week.
It's pretty good, I'm not gonna lie. You need to watch it.
Really? Is this scary? Yeah, no, me too. Definitely. And I'm still ready.
Like, there's like a real mix of like monster like going better. And like zombie
All right, so most of you have it, so let's go ahead and keep going here. When you open up your file, you should notice the following. State variable with all the states in the US, region variable. Now for you, yours might say 1, 2, 3, and 4. For your region variable, do you have regions or numbers?
Numbers.
Numbers, so we're going to change that. You should also have a density variable. This density variable is the density of dentists in each state. So it's the number of dentists per 10,000 US population. Okay, so the number of dentists per 10,000. That's density for 2016. And we also have Medicaid, that's the proportion of dentists who are Medicaid providers. And then Kids Prev. Kids Prev is the proportion of kids who are receiving preventive dental care in the past year. So in 2016, they asked the families, has your kid had preventive dental care in the past year? It's either yes or no. So when they surveyed, this number here is the proportion of families who are saying yes, their kid has had preventive dental care or had a visit in the past year. Okay? So our goal is to try to determine, or at least to characterize, what the U.S. looks like in terms of the density of dentists throughout the U.S., then later to characterize what the U.S. looks like in terms of the proportion of kids receiving preventive dental care for the whole U.S. But we have this region variable, which we're going to try to see, is the U.S. homogeneous or heterogeneous when it comes to the proportion of kids receiving preventive dental care? Meaning, whatever statistic we get for density and proportion of kids receiving preventive dental care, is it the same in all the regions of the U.S. as the same U.S. statistic, or is it different? So we're going to show you how to do that. So first, let's change our region variable. I'm going to bring up the slides. There we go. Here are 4 regions. The West will be for number 1. Number 2 gets converted to Midwest. Number 3 gets converted to South. Number 4 gets converted to Northeast. Okay? So West, Midwest, South, Northeast. How are we going to do that? When you double click on the region variable, so right here, just double click on that region tab, the region variable. This window should pull down. Does it pull down for you?
Yes.
Very good. Once it pulls down for you, over here in the levels, where you see the number 1, get rid of 1 and put
West.
West. Get rid of 2 and put Midwest. Get rid of 3 and put South. Get rid of 4 and put
North.
East. Half right. Good job. Good job.
Wait, what was it?
Okay, so number 1 is West. Number 2,
Midwest.
Midwest. Number 3,
South.
South. Number 4,
East.
Northeast.
Oh, Northeast.
Northeast. Because the Eastern Seaboard is everything from Rhode Island, Vermont, all the way down to Florida.
Do we press enter after that?
Right, so once you change these levels, if you want to get rid of this window, you simply click on this up arrow, and this will disappear so you can see more of your data again. Okay? Anyone having challenges, difficulties? Okay, everything is pretty simple so far. Grab someone near you in case you're having challenges, and if you guys aren't able to solve it, I'll pause and see if we might be able to solve that for you. Okay? All right, so once you make those changes, update those changes, you should notice a change in your data. Do you notice a change in your data?
Yes.
So it's not 1 through 4. Now you have Northeast, South, Midwest, and West. Fantastic. You'll also notice up here, I just want to make sure that you're tying this together with our lecture from before, you can specify for the program what kind of data that variable is. Now, Midwest, South, Northeast, West, is that nominal, ordinal, or ratio / continuous? It's nominal. They differ in name only, not in quantity. They just differ in name. So make sure that this is specified. Okay, and for the purpose of this course, ratio and interval will be known as continuous now. Continuous. A continuous variable is a variable that you can keep taking half, keep taking half, keep taking half, infinitely. Okay? Discrete is 1. 1 is a 1. And your next number is a 2. Your next number is a 3. These are discrete whole level measurements or whole increases. Continuous is, well, from 1 to 2 I can get 1.5. Between that I can get 1.25. Between that I can get 1.07, etc. Okay? All right. So let's start not with the kids' prev. We're going to start first with the density of dentists. So I'm going to bring up my Jamovi again. And now in Jamovi, I want to tell Jamovi Now I want to start looking at some basic statistics, the descriptive statistics. So up here where it says analyses, make sure you click on analyses in case you're in data. So I'm going to click on analyses. Then I want to tell it that I want to explore the data. See the far left?
Mm-hmm.
Explore. So click on explore.
Descriptive.
And descriptives. Huh. Huh. Not very interesting, right? Not yet. So we want to take our, so here we tell what variable we want, and we want to take our density of dentists in 2016 and move that over into the variables list. Move that over to the variables list. When you do so, right, you should get an automatic update to your descriptives table. So you don't have to go to Excel to build this. It's right there for you. Let me see if I can move this up so we can see that a little bit better. Right. That's better. Do you get a descriptives table like this? Yours is smaller. The reason why yours is smaller is because we have less options chosen. So I'm going to go ahead and determine the quartiles of standard deviation.
We have minimum and max.
You have min and max? Okay, let's take min and max. And I'm going to turn everything else off. Now do you get something like this? Very good. So what's our descriptives table telling us? It's telling us here's our variable, density of dentists in 2016. We have 51 states or region participating. One of them is missing this measurement, so you might want to go back and find out which is which. But if we look at the mean here of 5.85, what does that tell us? What does that 5.85 mean? Right. So
that's how many dentists you have in that region?
per 10,000. This is the average number of dentists per 10,000 in the United States in 2016 as measured by the CDC. Okay? What's the median number of dentists per 10,000? 5.46. You did this. So you got the data, right? So we downloaded the data from the CDC, we put it into a CSV file, imported it into Jamovi, and now you're looking at the basic descriptive statistics for that variable. Okay, so the average number of dentists per 10,000 is 5.85, median is 5.46, minimum is what? So there's one state where their proportion, or at least their density of dentists, is 4 dentists per 10,000. There's another state in which their density of dentists is, what's the max there? 8.85. Okay, so would you say that the US is homogeneous? Homogeneous with respect to density of dentists? No. I mean, this is a pretty big range. This is a pretty big range. One region has half the number of dentists per 10,000. That's pretty big. It's a pretty big range. Okay, so let's try to understand this a little bit further, because all we have is mean and median, central tendencies, but not much for dispersion. So how do we add dispersion? There are 2 things I want you to do. Go down to percentile values, here on the left-hand side, percentile values, and select quartiles. A quartile splits a distribution up into 4 equal groups. A median, also known as the 50th percentile, splits the distribution up into 2 equal groups. But a quartile splits it up into 4 equal groups. Okay, so we're going to ask for quartiles. We're also going to ask for standard deviation and variance. Okay. and skewness and kurtosis. Now, what are skewness and kurtosis? Skewness tells us whether the distribution is asymmetric. So the closer you are to a zero value, the closer you are to a symmetric distribution. But if your distribution is asymmetric, it could be asymmetric in the sense that you have some really low scores dragging the mean down, right? So that's a negative skew. Or you can have a positive skew where you have some fewer really high values dragging the mean up. Okay, so if you get a positive skew, you're going to get a positive value there for the skewness. If you have a negative skew, you're going to get a negative number there for the skewness. And the further away you are from zero, the more skewed that distribution is. Kurtosis tells us about how flat or pointy the middle of that distribution is. Okay, so the more peaked that distribution is, there's a higher kurtosis versus a flatter kurtosis. Okay, where it's a nice spread out distribution. Okay. And then finally, the normality, the Shapiro-Wilk, tells us whether our distribution is normally distributed, bell-shaped, one hump, symmetric around its mean, or not. Something that's not symmetric, or not normal, sorry. So let's go ahead and select that. And over the coming weeks, we'll understand that a little bit better. Go ahead and select that. Now we go back and look at our descriptors table and look at what we've added. So the standard deviation now to go along with that mean is 1.14. Okay, and the units are the same for that mean. The skewness is 0.739, so there's a positive or negative skew here. A positive skew. And if we look at the Shapiro-Wilk value here, this Shapiro-Wilk value is 0.007. Now this is a probability. Probabilities range between 0 and 1. But a p-value is a special kind of probability. It's called a conditional probability. So it's a probability that comes with a condition. And the condition is this. This p-value says, what is the likelihood for this test? What is the likelihood that the data is normally distributed, right? Or what's the likelihood that you would get the results that we're seeing if the data was normally distributed? Is that a low or high probability? It's low. So this is saying the likelihood that you would get the results of what we got if the data was normally distributed are low. So we're going to have to reject this assumption that the data is normally distributed. I don't expect you to memorize this or know this right now. I'm just going to keep doing it every week until we get to the point where I'm saying, okay, now you need to know it. But because I've been saying it for about 5 weeks, now you know it. Okay, so this p-value is a special kind of probability, a conditional probability, where we're saying it's conditioned on an assumption. And the assumption here is the data is normally distributed. This is saying what's the likely that you would see what you're observing if the data was normally distributed? Low. It's very low, which means throw out that assumption. Now all of this is conceptual. You have no idea what we're talking about until we actually start looking at the data. So now, let's start building some figures. In the bottom we see plots. Bottom left-hand side we see plots. Let's ask for first a histogram. Okay, go ahead and click on histogram. And what you'll note is on the right-hand side, you'll see what's called a histogram. Mm-hmm. Now with this histogram, we can see that the data, it doesn't take this bell shape. In order to understand that a little bit better, click on density. And the density gives us a cumulative function for what the shape of this distribution really looks like. So when you click on density, you now get this line. And this line is the cumulative density function that shows us what this figure actually looks like. Okay? So what we see here is that the data is not normally distributed, where we have one hump in the middle and kind of the data sloughing off to the left and sloughing off to the right, these nice shoulders. No, what we see is that the data has how many peaks, possibly?
2.
At least 2 peaks. At least 2 peaks. So with at least 2 peaks, this data is not normally distributed. A normal distribution has only 1 peak. Only 1 peak. So one of the things that we're going to say here for the US is that when we sampled from the US to try to understand the density of dentists, the US is probably made up of more than one population. A population that has a peak here and a population that has a peak here. So the US is not homogeneous when it comes to the density of dentists. It looks like there are at least two populations here when it comes to density of dentists. A population with a peak here and a population with a peak here. Yes?
Do we need that?
Yes?
My computer doesn't show it. Does anybody else not show it?
It doesn't show it like because it's you got to scroll or
No, it just doesn't have it up.
doesn't have the option at all.
No, it does. There.
It just doesn't show it. Try and click on those buttons.
Oh, after you click on density, it did not show it. Is this for everybody?
No.
She doesn't even have.
Is it working on it?
She doesn't have the histogram there.
You don't have a histogram at all. Now, what do you have up here? Do you have density?
Here it is.
Oh, nice.
Oh.
That's just called debugging. Yes. Yeah, homogeneous. Homogeneous. So homogeneous means that there would be a similarity in the what's driving or what's characterizing this distribution. That's the layman's definition.
So hetero means one.
Heterogeneous means that there would be differences in what's characterizing this distribution. So homogeneous is the same factor. Heterogeneous, different factors. Yes?
So if it's homogeneous, would there only be one bell curve or is
If it was a homogeneous population, there would be one bell curve, right, with one peak. But because it's heterogeneous, our sampling is telling us, ooh, it looks like you probably sampled from more than one population. Now, because this is the entire US, this data, that means that we probably have more than one population in the US. Here's one population with a peak here, and here's another population. You put them together, you get something that looks like this.
so it's heterogeneous?
Right. So, for example, salary in the US, you might be bimodal in the sense that you have one really skinny but a normal distribution up here, right? That would be the 1%. Then you'd have everybody else down here with another peak here. But it'd be bimodal. You have people who are in that 1% category, and you have the people who are in that 99% category. Within that 1% category, there's a distribution, normal distribution. Then within that lower, the 99%, there's another distribution with one middle. So if we put them all together on the same figure, down here with income being here, you'd see one distribution here and another distribution there. But it'd be for the entire US.
So as long as there's more than one, it's heterogeneous.
If there's more than one, we're saying this is a heterogeneous population. It's not a homogeneous population. And the reason why that's so important is, remember, we're dealing with uncertainty and we're not dealing with all the data. So if we're saying I need to infer something about the population based off the sample I have, well, if you had something like this, who are you generalizing the data to? Is it this population or this population? So you can't generalize data from your sample if you have evidence that you sampled from more than one population. You have to go back to the beginning and structure your sampling so that you only have one sample, one population. If you have more than one, you got to stop because we don't know who you're generalizing the data to. Yes?
And we don't know if this is based on regions.
We think it might be based on regions. That's why we collected the region variable, because we think it might be based on region.
But we cannot specify.
Well, we can ask because we've got region. You're ahead of me. We're going to ask about region. We're going to stratify all the results by region and see if region helps us to deal with this. It might help, it might not help. Right? But that's one step to do it. You're doing exactly what an analyst would have to do. Here's your data, now you need to break it down. How are we going to address the fact that we're dealing with more than one population? Is it based on income? Is it based on geographic region? Is it based on immigrant status? We don't know. We don't know what this is based on. What do we think density of dentists would be based on? Region, income, Could be those who are in the middle of the U.S. versus those who are on the coast of the U.S. Right? Those could be, that might explain density of dentists. That the density of dentists is higher on the coast than it is in the middle parts of the region.
What about the population of the states?
Could be population as well. But we're trying to adjust for population because we're looking at density. So the number of dentists per. So we're adjusting for population. We're removing that as one of the confounders. Yes. These are fantastic questions, by the way.
When we did the first part, before the histogram and everything,
Yes.
we saw that the maximum and the minimum were different. So
Yes.
right from there, we knew that there was not, how do you call it?
Homogeneous versus
Homogeneous,
heterogeneous.
right?
Yeah, that's your first clue that you have some heterogeneity in the sample. The fact that the minimum was so low and the maximum was so high is double. So your first clue that there's probably going to be heterogeneity here was, why is there this? Why is the min and max so high?
Okay. So the rest of the steps we took, it was pretty much to see where was the difference, right?
Well, our first step is to characterize the U.S., and that's just factual data. You want to put a figure like this and say, look, this is what the distribution of density looks like for the entire U.S. Okay. Is there heterogeneity? That's what you do the discussion. But right now in the results section, you simply just lay out all the results, lay out all the facts. Here's a mean, median, min, max, etc. Here's what the distribution of the density looks like. We don't characterize it yet until we start talking about why we think it might be that way. Okay. So if we move on to box plots, go down here to the middle where we ask for box plots, and I want you to select box plot. When you select box plot, you might need to scroll. You should get a figure that looks like this. So this is another diagram of the data that you have that's populating this histogram, except it looks a little bit different. So what we do with the box plot is we show you where the minimum is, remember that 4.12, where the maximum is, remember that 8.85, and here, this middle box shows us the 25th percentile, 50th percentile, and 75th percentile. So this box covers the middle 50% of the distribution. It also gives us a central tendency. The 50th percentile is also known as the median. Okay? So 25th percentile, median, 75th percentile. And we know that this is skewed because this whisker is longer than this whisker. We can also see that the median isn't in the middle of the box. So we know that there's a skew here, a positive skew, because all the scores tend to be, well, you have a skew going this way, but the rest of the scores tend to be lower here. Right? But this box plot is a nice way to kind of show the distribution of the data in a way that is a little easier to understand than the histogram. Now, where is the data in this box plot? Go ahead and click on violin and data in that box plot. So over here, click on violin and data. Now the violin part gives you, it's just like the density. It kind of shows you where the weight of the distribution is. Okay, so here we can see that as we move down here in the distribution, this is where the weight of the data is. And as you move towards the top, okay, we see that the scatter of the scores are here, and there's a bit more here than here at the top of this box. Okay. Now with the R code that's driving this, you can actually manipulate a lot of this figure so you can make this more transparent, so you can see the data better. But again, this is all really kind of meaningful in the sense that with a few clicks, you've been able to get your data into a figure that lets a reader know I have a skewed distribution of density of dentists in the US. Most of the density is at the lower end. We have a few skewed towards the higher end, where the least are in the middle. So for an analyst who's trained to look at this, this is fantastic. They now have an understanding of density of dentists in 2016. In fact, the fact that you see a sort of like a bubble here and a bubble here also gives indication that we have two separate populations contributing, as opposed to just one bubble. Okay, this is all very interesting, and it's a great foundation for us to be able to characterize the U.S. But our real goal here is to try to determine what to do in case the U.S. is heterogeneous and not homogeneous. We have a variable that we've collected that we think is going to help us understand some of the differences in the U.S. It's called this region variable. I'd like for you to take this region variable and move it into the split by window. Move it to the split by window. When you do so, everything that you've done before is now stratified by the region variable. Okay? Should be anyway. Oops. I think yeah, hang on. I'm going to open up a different file since I unwittingly got rid of my data. So I'm going to catch up with you for one. I'm going to put that down. We have the West. 2 was the Midwest. Thank you. 3 was the South. 4 was the Northeast. I'm going to get rid of the window. I'm going back to Explore. I'm going to put density back into the variables. I'm going to put region to my split by. And now I'm going to select all the information that we needed before. Followed by the plots. Okay? So if you go back up to descriptives, you'll notice now that for your mean, you have 4 means, one for each of the regions. You have the West at 6.35, Midwest at 5.56, South at 5.26, Northeast at 6.63. So Northeast has the highest density of dentists. The South has the lowest density of dentists, according to the mean. I think the median would be a better measure of the middle for the distribution because we established before that it's not normally distributed. So when the data is not normally distributed, that means the mean and median and mode aren't close to each other, the mean is not a good measure of the middle. The median is a better measure of the middle. So let's look at the median. Median says that the West and Northeast are at 6, or they're above 6 in terms of density of dentists per 10,000. South is at 4.92. Okay? Significantly lower than where the other regions are in terms of density of dentists. Be easier to appreciate, though, once we start to look at the figures. So scroll down, and let's look at the first plot. West, Midwest, South, and Northeast. First question you want to ask yourself when you look at the West is, does it look like the West is made up of one population? No. It looks like the West, with all the states that contribute to the West, I think there are 17 states. Very simple. We go back up. And no, 13. 13 states contributing to the West, 12 to the Midwest, 17 to the South, 9 to the Northeast. But if you look at it, it says that the West, with all the states contributing, does not look like it's homogeneous. It looks like it's a heterogeneous mixture of states. So this is where we have to have some caution when we think about interpreting the results from the West. What about the Midwest? Does it look like it's homogeneous? More. A lot more so than the other regions. So one hump there kind of looks like it's normally distributed. Okay. What about the South? One population? No. It looks like there's more than one. So we have a peak here, another peak here. What about the Northeast? No, not one population. Looks like it's heterogeneous. You've got a peak here and a peak here. So not only is the entire U.S. different, heterogeneous when it comes to density of dentists, but if you look at within the regions, there appears to be heterogeneity as well, except for the Midwest. The Midwest appears to be more homogeneous when it comes to density of dentists. If you look at the box plots for density of dentists. Now we have a greater appreciation of where there are differences for the middles. So if you look at the horizontal bar in the middle of the blue box, which is where the 50th percentile or median is, you can see that's highest for the Northeast, followed by the West, then the Midwest, and then the South. So here we can see that, yes, the South has the lowest density of dentists per 10,000. So as a policy analyst, if you're looking for areas in which you might want to improve, or if you're looking for factors that might be related to why the kids' oral health may not be as great, it might be because the density of dentists or access might be lowest in the South than it is in other regions. A couple questions.
Question, sir. So the peaks, for example, on the west.
Peaks on the West, yes.
What signifies the peaks, or what do the peaks mean?
Okay, so that's frequency. So for all of these, if you look at the density here on your x-axis, right? Density of dentists, low at 4, highest is here at 10. This y-axis is frequency. So it's the number of states or regions who are near or at that density level. So when you get a peak there, that means most of the states or more of the states in that region are kind of at that level. If it's very low, it means there's either no state there or very few states there. Okay? So that's what the y-axis is. It's the number of states or number of regions contributing. Good question.
Thank you.
Back to our box plots, so we can see here that which region has the most narrow interquartile range. Now, interquartile range is a difference between the 75th and 25th percentile. The South has the lowest interquartile range. So the South has the most narrow middle 50%, which might, for some of you, say, well, isn't that kind of a measure of homogeneity, that there's very little range for at least 50%? And I would say yes. And interestingly enough, or ironically, the South also has the biggest range. So look at its max, that 8.85, and its minimum, that 4.19. So both the min and the max come from the same region. So the South is a very interesting region within the U.S. in the sense that, one, it's fairly low in terms of density of dentists, but they also are the region that has the highest density of dentists. So if we wanted to look at the impact of access to care to the outcomes of care, the South might be one region which want to do so, because they seem to have a nice range of access. Now we just need to look at outcome to see if there's a relationship between access and outcome. Follow me so far? And all of this you're getting just by figures. This is the power of visualizations of data. You don't have to really run a lot of fancy statistics to be able to generate really decent and meaningful statistical questions. Okay? Now for your assignment, you're supposed to look at Kids Prev, the proportion of kids who are receiving preventive dental care in the U.S. And you can actually accomplish much of that right now, just by moving Kids Prev over to where?
Variables.
That's right, move it over to variables. Look at that, you're 80% done with your assignment now.
So if we move dentistry back up.
No, because in your assignment, I want you to characterize density and proportion of kids receiving preventive dental care. Right. So your assignment is 80% done. Now you just need to kind of pull the tables and figures into the Microsoft document. Just kind of write a little bit about what you see. Okay. So let's take a quick look at what we see for Kids Prev. And I'm just going to look at the figures with you. One population for kids receiving preventive dental care in the West? No, there's 2, maybe 3, but 2. Yeah. What about for the Midwest? Wow, maybe 4. Maybe 4. So when it came to density of dentists, very homogeneous. When it comes to proportion of kids receiving preventive dental care, all over the place. Why? We don't have the data yet to be able to address why, but now we're starting to we're starting to try to put together A and B and say, look, if this is the situation for A, then why are we seeing B? What about for the South? At least 3 maybe, but definitely more than 1. And what about for the Northeast? At least 2. So for density of dentists, only the Midwest was a region in which we saw homogeneity within that region. But for proportion of kids receiving preventive dental care, we see that none of the regions is homogeneous. And if we take region out, this is where we can look at the whole U.S. as its own population. Take it out. Here's what we see for kids Prev. 1 population? No. Looks like here's a peak and possibly a peak here. Okay, so when it comes to density of dentists, the U.S. is not homogeneous. When it comes to proportion of kids receiving preventive dental care, the U.S. is not homogeneous. So when we hear a lot of people saying, look, we need to have a national health care plan, maybe, how would we do that when the U.S. is so heterogeneous? The regions are so different in terms of the factors that are related to providing decent health care. So it's not a political issue. Maybe this is more of a statistical issue. Right? They're so different. How would we actually do that? And I think they understand that. Let's not be naive. They do know this. But I think for the rest of us who are participating in that whole healthcare argument or debate, we too need to be educated. So now we understand from an oral health standpoint, density of dentists is not uniform. 1 number for the whole U.S. cannot be applied to the whole region. Take a look at kids and their access to preventive dental care. It's not uniform. There's heterogeneity. So when we take all of the factors that matter for healthcare, or let's say oral healthcare, we're looking for homogeneity and heterogeneity. And these kinds of figures help us to understand whether the U.S. is homogeneous, where 1 solution might work, or heterogeneous, where we might need more than 1 solution to work for the entire U.S. Okay, so your homework assignment is to characterize what you see for the whole U.S. and by region for these 2 variables. And you submit that before we meet for class next week. So every week we kind of end with a Jamovi run through the data, and then you kind of add a little bit more to that and submit by next week. But I'm hoping that by the end of this course you become very confident, very familiar with using little programs like this to look at your data and understand what your data is telling you. Good. Yes?
So basically this course, we're just going to be understanding how to read this stuff.
Yep. Not just read it, build it, and then interpret it. Because right now you did this.
Are you going to post what the homework is?
It's there. There should be an assignment.
Oh, okay.
And that assignment asks for this from you. Right. We essentially did it here in class. If any of you were recording, a lot of the things that we were saying, those are things that you would include as, this is what I see. When we characterize what we see for the whole U.S., characterization means what's the mean, what's the median, what's the central tendency, what's the dispersion, what do the figures look like? Does it look like there's 1 population homogeneous or more than 1 population heterogeneous? And you do that for kids Prev, you do it for density of dentists, and that's it.
So that's not in the book, this first assignment?
In the book? No. It's on Canvas.
Yeah, I see.
Yeah. And if you have any questions, don't hesitate to email me. Yes?
Does this save? Do we have to click a save button, or like when we exit? Or?
I apologize.
Okay.
Every time you're doing something, please save. There, in R, there is an automatic save, but I think in the Jamovi program, there is not an automatic save. Okay, so you might have to save periodically.
Control S.
How do you save it on here?
Well, go to the horizontal bars, and underneath the option of opening.
It says that it won't let us save it because we have a demo.
No. Go back when you download. You should have the live full version. This is open source and free. It's open source and free. You should be able to save.
It says like not currently available in this demo.
Okay, so I gave you the same link in which I downloaded the software. I'm saving just fine. I'm doing the same thing with the pre-doc class. They're saving just fine. Where are we getting your version from?
She got it. Are you going to save this?
There's only one person that can save?
I save it.
You say? Oh, so some of you can save.
Yeah.
She's got a Mac. And
I'm on a Mac as well. I run both environments. I checked thoroughly. Both environments work for me with the same link. So here's what I would do. Because it's really easy. I would go back, re-download, and when you download again, it'll say, hey, do you want me to get rid of the old version? Say, yeah, go ahead and get rid of the old version. It'll install the new version. Try to save again. Okay, but go ahead and go back to the link, download.
Download the
Let me
CSV.
no, not the CSV file. You're going to save a Jamovi file. The CSV file was just to bring the data into Jamovi. But what you want to save is not the CSV. You want to save this Jamovi file. That's for this app.
Like, it says, like, when you're on the Jamovi website, it has that area for you to click download.
Right, so when you go to Jamovi download, right, it's like go to Google, Jamovi, and it takes you to the link, and it says download. Click on download, and in the middle you'll see this little blue bar. It will automatically recognize what your OS is. And in that little blue window, that little blue bar, just click on that, and it will download the version specifically for your OS. And it's a full version, full rights, full privileges, everything. So download that guy, and then when you bring in our file that we worked on, you should be able to save that. Okay, but you're saying that for some of you, it says you've got a demo version and it won't save. Now, does it say that you can upgrade to a full version? All right, who's got a demo version? I want to take a look at that.
Right here.
Whoa! Wow, everybody? Even the people that are saving? Who's able to save? Is yours a demo version too?
It doesn't say anything.
Yeah, it doesn't say demo version. Sorry?
Where did you go?
HP? It doesn't.
All the ones you wrote there.
Okay,
She's
so
got a Mac and she downloaded it.
yeah.
It works?
Let me see who's got an HP. I want to see the HP. Yours
Yes.
demo, and you're able to save or not?
I'm able to save. Yeah. So.
Okay, HP, but not able to save. Can I see that? Who is that? You guys up here? Is it Dan?
Yes.
Saving or no?
I have mine just says this.
Not currently available in this.
It wasn't letting, like, we had to drag and drop the file into it too. It won't let you, like, upload a file.
Okay, so this is.
Yeah.
This. I don't know why it's called. Are you running an emulator on here?
No, when I downloaded it, it popped up the hard drive thing, and then I just downloaded Jamovi that way.
Okay. So let's go here. Close this out. Do you mind if we go to...
Yours did.
For summer break.
It's 1176. What's the focus? I know. One part in the whole classroom. Well, and here.
I just pushed the big blue one. I didn't select anything. That's
Oh. Let's see what it says. And it tries to reinstall, and then we'll go back and try and save again.
Okay.
One show of hand again for those who are not able to save. Keep your hand. Okay, keep your hands up. Keep your hands up.
It is.
I'm just trying to think of what the common
I
denominator
have
is here.
like one, maybe I do it. I don't know, like, so I downloaded it with this big blue
Yeah,
button.
yeah.
Maybe, like, they have options down here that I didn't see, like, you can
tried
specifically click.
It does
Oh,
the
it didn't
same.
change
It does.
it?
It downloads at the same time.
Darn it. I don't know then.
I'm trying to think what the
Sorry,
comment.
that happens.
So,
Wait, would it work Mac?
Maybe it's a Mac thing.
no, because well, those are Macs. Who's running a PC? No PCs.
The PC,
Or-
but I was able to download it.
HP?
Yeah.
Sorry?
Just only the HP. If you guys have an HP and it's saved, raise your hand.
It's saved.
HP
And it's saved.
and you saved.
Yeah.
Okay. Okay, show of hands of who could not save. Okay, so again, that's the majority. Keep them up. I'm just trying to think of what the common denominator might be with your hands raised. I've got a Mac too. I've done this on Mac, PC, laptop, desktop, all just fine. I've given you the same link. I'm just trying to think.
Well, we all had to give our MacBooks to computer services. Maybe they did something.
Yeah.
Okay, but for the ones who didn't.
No one. She thought that she did, but it didn't save for her.
Oh, so it did not save. Okay. It did not save for you.
It did.
Oh, it did.
She's
Okay.
she's not into HP.
HP.
So the only one that's saved is an HP.
And Mac. He's a Mac. No, he's an HP.
Yeah, I don't think any
What's different about your setup from the pre-doc setup? It's better. No, because we did this yesterday and they were all able, not all, many of them were able to save.
But our laptop was changed from the school, all of us.
That has nothing to do with the program.
Yeah, because the program is saying it's a demo copy, and why would it route you to a demo copy?
Did you save it as a file?
So, is yours nearly?
Yeah, it's almost there.
Okay, yeah, because I want to try that. Yes.
I re-downloaded it and tried to do it again, and I still didn't.
Same thing.
30 minutes.
Yeah, this is what pops up. And then I open this.
And what I try to do is roll back to see if a previous version is available. And if the same issue happens on the previous version, then it's
I'm sure you want to open it.
yeah. Yep.
Maybe that's what I thought.
If it happens with the previous version, then I think it's
What I use from anyway, right? I'm in Safari. What do you use?
It's like a bar. Yeah.
Then you try to like,
That's so No, I want to have
like you're like trying to have us open. And like,
Thank you for your thoughts.
It's just like,
It said that it's not.
One second. All right. Do you have a USB? Yes? Oh, yeah, that's fine. I'm more concerned about long-term rights. Yeah, so yeah, you can screenshot and send that to me. That's fine. Actually, no. I'll need to make a change to the Canvas because right now it's accepting only PDF and Microsoft Word. So I have to open up and accept JPEGs as well. But what I want to do is I want to take my download file, have someone use my download file on your computer and see if that works. You've got a PC.
Yes. Wait, so did you want to put it on a USB?
Yeah.
Okay. Because I know Macs have a weird extension.
USB-C. I don't know. You do? Yeah.
Oh. I have a USB here if you want to.
All right. Do you have this?
Yeah.